Zoom? Oh, come on, where is Zoom? Okay, sorry, I pressed some button and okay, now I can see again Zoom. Yeah. Okay, I think we can start now. Yeah. So good afternoon, everyone. Welcome to the NITheP webinar. And today we have again Dr. Sanjaye Ramgoolam with us. And I hope that all of you heard his previous NITheP colloquium on Monday. On Monday, so you should still have the general setup of what he is going to speak about today in mind, because today he will speak on a similar topic, but a little bit more technical, I guess, or a little bit more for the interested audience. Yeah? Just two sentences to introduce the speaker in case you were not here on Monday. Sanjay is a reader at Queen Mary University of London, and he's a visiting professor at WITS, where he's been working with Robert Emelo Koch and others. So that's the link to South Africa. Yeah, and previously he's been he had postdoc position at all prestigious university in Princeton and at Brown. Yeah, and he's also an advanced fellow of the STFC. Sanjay, we are very happy for you to be with us again today, and we are really looking forward to your webinar. Yeah. So if you want, if you are ready, you can start sharing your screen. And while you do that, I briefly introduce Ilya, but although by now everybody should know him because he's always in charge of the question and answer sessions. So Sanjay, please, if you would like to share your screen, you're most and welcome to start with your presentation. And you know, needless to say, please make use of the question and answer facility to ask questions. And since there are not so many of us, Ilya might also give you the right to, if you raise your hand or indicate that you want a question, to ask your question in person.
Okay. Can you see my screen?
Yes, we are in business. Yeah.
Okay, perfect. Great. Thanks a lot, Francesco, for the invitation and for the introduction. Yes, this is indeed a follow-up of the colloquium on Monday. And the title today is going to be Kronecker coefficients and lattices of bipartite ribbon graphs. And this is based on the same papers I mentioned last time with these collaborators, Joseph Benjeloun, Paolo Mattioli, Gareth Kemp, in these papers. The most recent of these papers is a few weeks ago. I'm going to start with an introduction, which will be a little bit of a review of some of the things that I said at the colloquium. So in the colloquium, we discussed, the notion of quantum mechanics on a Hilbert space, which has some additional structure of an associative product. So it's what I was calling quantum mechanics on combinatoric algebras. So we have algebras, which are vector spaces with a product, and they also have an inner product, so a scalar product. But what is different from a normal, ordinary Hilbert space, well, it is a Hilbert space, but it has the additional structure, which many Hilbert spaces don't have. This one has the additional structure of an associative product. So, but it is a Hilbert space, just happens to have some additional structure. A nice example of such a combinatoric algebra is the group algebra of Sn, the symmetric group of all permutations of n distinct objects. And this group algebra, because it's defined as formal linear combinations of permutations, which I denote as sigma, it has a combinatoric basis, which consists of these permutations themselves. And last time we talked about a Fourier basis, which is labeled by Young diagrams, which come from representation theory. And the way the Fourier basis looks like is you have some elements QR, Ij, which are linear combinations of sigma, but they are linear combinations which are labeled by a Young diagram R. And for a Young diagram R, we have a representation, a vector space where Sn is represented. Representation has a dimension which I call d sub r. And these I and j indices run each of them from 1 to d sub r. There's a total of d sub r square here for each fixed r. And if you sum over all r, you get exactly sum over dr square, which is n factorial. So which is the number of permutations. So you have two different ways of writing bases in the same algebra. And that sort of can be thought about as a Fourier transform on this non-abelian system, or this associative algebra. And we mentioned that algebras related to the group algebra of Sn and this notion of Fourier transform between them. This whole setup is useful in enumerating tensor model observables and calculating their correlators. So what are tensor models? They are models defined in terms of some, if you like, a random variable labeled z, which has 3 indices I, j, k. Each of these indices runs from 1 to n and is an arbitrary general integer. Often we're interested in large n. And this transforms in V tensor V, where this is the fundamental of un. Okay, so there's n cubed degrees of freedom here. And this is a conjugate variable which transforms in the conjugate representations. In a tensor model, you're interested in doing an integral over this z variable. This is some standard measure on these complex variables. And then you have an exponential here. And then we are interested in looking at gauge invariant functions of z and z bar. By gauge invariant, I mean functions which are invariant under un cross un cross un. The observables, these observables or gauge invariant functions, we are interested in the polynomial functions, and the polynomial functions can be organized by degree. So to have something invariant, you need the same number of z's and z bars. And how many that is called n, which is the degree of the invariant. So for example, if you have here a simple invariant, I've switched from phi to z here, from z to phi, but you can think of it as z. So if you contract indices, if this is in v, this is in v bar, you contract, you get an invariant object. A sum here is implied. You contract this one, you get an invariant of the second. Contract this one, you get an invariant of the third. So you get something which is invariant under un cross un cross un. And these invariant objects, we recalled, can be associated with colored graphs in this way. So this is z bar. The indices are lines, and because there are 3 different kinds of indices, we have colors. And the general gauge invariant observables can be labeled by a triple of permutations. So if you take invariants containing n of these z's and n of these z bars, you have to contract the indices. So you're going to have, for the first index here, you're going to have I1, I2 up to In. And in order to build an invariant, you have to take these indices and contract them with the indices coming from the conjugates. But there is an arbitrary ordering that reordering that you can do. And that's parameterized by a permutation sigma 1, which is a permutation in Sn of n objects. So here's what the invariant looks like. You have I1 up to In, here I, the permuted one up to the permuted n. And then you have similar sigma 1, sigma 2, sigma 3 for the 3 colors. Now, if you choose any such triple of permutations, you get an invariant gauge invariant object. But that doesn't mean that the counting of invariants is so simple that you just have pick 3 permutations and factorial cubed. It's not that simple. The reason it's not that simple is because some of these triples are related to other triples. If you take a triple and you multiply it on the left by the same permutation gamma 1, or multiply on the right by the same permutation gamma 2, you get the same observable. back in this picture corresponds to gamma 1 and gamma 2 corresponds to permuting these guys and permuting these guys, which is leaves you with the same object because these are bosonic variables. And permuting, as you see, if you permute this and that, you're moving the black and the blue and the red simultaneously. That's why this gamma 1 acts on all three of these sigma permutations. So these equivalence class, so what are we doing here? We're thinking about three permutations, and we are saying that some triples here are going to be in the same class, same equivalence class as some other triples, which are related by these equations. And such equivalence classes are called elements of a double coset, triple power of Sn modulo the diagonal subgroup. And it is known that the space of functions on double cosets of this kind, G mod H on the right and the same H on the right and left, form an algebra. In this case, we're going to call it K of N. Okay, so here's a discrete object, this double coset. How many elements are there in that discrete object? That's, I'm going to go curly N of little n. Using this idea of Fourier transforms, there's sort of two ways to describe how many there are. One is in terms of partitions of n, number of ways of splitting n into sums of positive integers. And for each partition, there is a quantity called the symmetry factor associated with that partition. You sum these up, you get the number of invariants, tensor invariants. I am assuming the big N we talked about is very large here. And then another way to think about it using the Fourier transform idea is in terms of Young diagrams. And you take three Young diagrams, all with n boxes. You think about, if I take a tensor product of them as Sn representations, how many times does the invariant appear in the decomposition of that tensor product? That's called the Kronecker coefficient. You sum the squares of these Kronecker coefficients, you get precisely the number of tensor invariants. Two ways to think about that. And we said the number of invariants is, the invariants correspond to these colored graphs. So the sum of Kroneckers is a kind of something you can concretely construct using colored graphs. And that raises the question, can you construct an individual Kronecker coefficient for a fixed R1, R2, R3, or the square of that in terms of graphs? So that's the question we address in this latest paper. And in order to address that question, we use the notion of Fourier transform on this double coset algebra K of N. So again, Fourier transform means there are two interesting bases. One we're going to call the combinatoric basis related to graphs, and another one which will be a basis related to triples of Young diagrams. For each triple of Young diagram, you're going to have an extra index.
Sorry, Sanjay.
Yeah.
I think Robert have a question, and he's welcome to ask the question.
Oh yeah, please.
Thank you. Thanks, Ilya. So Sanjay, my question is the following.
Yeah.
So you have considered a model here where you have a Z and a Z bar, both rank 3, and sort of one is the dagger of the other.
Yeah.
Question is there a generalization of this story where you have, perhaps you have matrices that are in bifundamentals of some of the groups together with the tensor, so you have this more general space of invariance. And in that situation, do we have an idea of what the counting looks like? So probably it's not a double coset, I don't know, maybe it is. And do we still have the Fourier transform notion?
It's quite general. Yeah. So indeed, the simplest case which we discussed last time was a one matrix model purely. The next simplest case is the two matrix model, where indeed there's a lot of work there, some of your own restricted shores, which have very similar structure. And if you combine multi-matrix with tensor, it is a very general idea. You always can express all of these kind of bases in terms of an algebra, and there's an associated Fourier transform. So for example, in the two matrix case, the combinatoric basis would be sort of necklaces with two colors of beads. And then this is the analogous thing that you know, well, which is something labeled by two Young diagrams and some multiplicity indices.
So do we know that it's always a double coset, or
in
would generally be more complicated?
I think in most cases we can formulate it in terms of a double coset.
Okay,
yeah,
that's quite a general part of the story.
I think it's quite general. It's not always most useful to write as a double coset. But even here, you see, I will find that the double coset can be simplified and expressed in another way, which is not manifestly a double coset, but still very useful.
Right.
I'm not sure it's universally true that it's always a double coset. I think one does encounter examples where it's not double coset. But what is quite always true is that in problems like this is that you have permutations subject to equivalences. That's completely universal in all problems that I have encountered of this kind.
And is it always obvious what the Fourier transform is?
Yeah, pretty much. Once you've written it in terms of permutations and equivalences, then because permutations define an algebra, the group algebra C of Sn, and then you can always find a subspace of some tensor product of group algebras. Whether that subspace is an algebra, that's another question. It's not always the case, but certainly some subspaces of tensor products of group algebras of Sn, I would say that's quite general in studying gauge invariants of multi-matrix, multi-tensor, whatever kind of model.
Thank you.
So, great. So in this particular case, we have this algebra K of n, and there is an interesting Fourier transform on it, and there's a combinatoric basis which corresponds to graphs. Now, if we think about these combinatoric basis elements, I will write explicit formulas for this in terms of permutations later, but these are some combinatoric basis elements. And then if you think about arbitrary real linear combinations, that forms a Euclidean space. And because the number of these graphs is n of little n, r to the n of little n, that's the real Euclidean space with that dimension, the dimension being the number of graphs you can write with n edges. Inside this Euclidean space, there's a lattice formed by those, the case where these coefficients are chosen to be integers. So that's z to the power n of n. So the outcome of thinking about, how to describe Kronecker's individual Kroneckers for a given triple in terms of graphs is that one has to think about the integer lattice generated that I just described, integer linear combinations of these ribbon graph vectors, which form basis vectors in the algebra. And this integer lattice contains many interesting sublattices. For each triple, R1, R2, R3, you have a sublattice of dimension C square. And you can also have sublattices related to C, which I'll describe later on. Simplest case will be to understand C square. So inside that lattice, we have this lattice exists inside a vector space. The vector space is also an algebra, and that lattice contains sublattices. And the sublattice can be constructed by looking at null vectors of an integer matrix. Now, that's a kind of nice thing that there's a lot of mathematical theory around integer matrices and integer matrix algorithms. And there are algorithms for constructing the null vectors of an integer matrix, and they are associated with the study of lattices. And in the study of lattices, there's something called Hermite normal form of an integer matrix, which exists for any integer matrix. And such techniques can be used to calculate the set of vectors which are annihilated by an integer matrix. So we will make use of that in order to give a concrete description of this sublattice. Now, from physics point of view, focusing on this particular combinatoric structure, why are we so interested in that? Turns out the reason for being interested in this structure, these three-colored graphs and permutation triples, there are many reasons from string theory. And this comes from the fact that this three permutation description can be rewritten in terms of, one description is in terms of permutation pairs. And there's an equivalence relation on those pairs. And associated with that description, there's another combinatoric object called bipartite ribbon graphs, which are also called dessins d'enfants, which have been studied by Grothendieck in connection with number theory. And there is another, related to that, there is another description in terms of permutation, which involves a triple. And that triple, which is different from the triple we started with, and that triple is related to the geometrical picture, where each of these equivalence classes is related to a branch cover. So a surface covering a fixed sphere with three branch points on the sphere. And these surfaces can be interpreted as string world sheets mapping to a target space sphere in a sort of in a topological string theory. So there are many reasons for being interested in K of n, and that's related to the fact that this permutation description can be reorganized into other things. So I'll talk about that. And then, so more about the physics, I started with quantum mechanics on combinatoric algebras. So the focus today will be quantum mechanics on K of n, which helps us formulate some constructive algorithms for Kronecker coefficients. And if we can realize such kind of quantum mechanics in the lab, and I'm happy to be giving this talk to a quantum information audience here, if we can realize this in the lab, then this can lead to quantum experiments which can detect non-vanishing Kronecker coefficients. So I'm going to say a little bit about that. And because of this connection to string world sheets, the graph itself corresponds to a string world sheet. But here we're doing quantum mechanics on the space of graphs. So one graph can evolve into other graphs. And that whole evolution should be thought of in terms of a quantum membrane world volume, because the graph is a string is a world sheet, but then there's time, the graph evolves, so the string world sheet evolves, and that defines a quantum membrane world volume. So we're going to talk a little bit about that physics towards the end. So the outline of the talk is that we're going to think about these colored graphs and this permutation triple, and then go to these other combinatoric objects, bipartite graphs and the Belyi maps. Briefly talk about that, the existence of the different pictures. Then we're going to talk about this geometric basis or combinatoric basis and the Fourier basis in K of n. Then we're going to use that structure to think about operators and Hamiltonians which exist in this algebra. So we're doing quantum mechanics where this is the state space, but it's also an algebra. So there are interesting Hamiltonians that come from the algebra itself. So we're going to talk about these Hamiltonians. And then when you're trying to solve for the eigenvectors of these Hamiltonians, there are integer lattice algorithms, which can help you find the eigenvectors. So we'll talk about how these integer lattice algorithms help us find eigenvectors, which in turn help us find sublattices in the lattice of ribbon graphs, which are related to C square and also to C. Then we'll discuss the physics of these things. Great. So we start with these permutation triples, and there's an equivalence relation, left multiplication. Sorry, there should be three here. Gamma 1, sigma 1, gamma 1, sigma 2, gamma 1, sigma 3, and gamma 2 on the right. So we have all of these permutations are in Sn. And this defines a double coset of Sn cross Sn cross Sn by left multiplication with diagonal Sn and right multiplication with diagonal Sn. So there's a typo here. There should be a gamma 1, sigma 3, gamma 2. Good. So we're going to use that triple. Now, so here's one such triple. So I take this one triple, and then I say, let me choose gamma 2 to be sigma 3 inverse. So multiply on the right by sigma 3 inverse, this becomes 1, and I get these permutations, which I'm going to call tau 1, tau 2. And now also what I can do, given this triple, I can apply gamma 1 to it. Gamma 1, gamma 1, gamma 1 here. And then after doing that, I can apply this other equivalence, which is where I'm going to choose gamma 2 to kind of cancel this. So it'll be sigma 3 inverse, gamma 1 inverse, sigma 3 inverse, gamma 1 inverse. Then this becomes 1 again. And what am I left with when I multiply by sigma 3 inverse, gamma 1 inverse? I'm left with this. So again, I have 1 here, and I have, sorry, this is a type of gamma 1, sigma 3, sigma 2, sigma 3 inverse, gamma 1 inverse. Okay, just take that, multiply by that. This is what you get here. So the upshot is that now we have this tau 1, tau 2, which are these guys, sigma 1, sigma 3 inverse, sigma 2, sigma 3 inverse, essentially the same tau 1, tau 2, and I am conjugating them. So now I've reformulated this. So this is a key thing to look at. There's a pair of permutations, and I'm conjugating them by the same permutation. And that's another reformulation of the same problem. We are looking at pairs of permutations, tau 1, tau 2, and any pair related to another one by simultaneous conjugation with the same gamma, I'm going to say it's in the same equivalence class. So these are known to describe bipartite ribbon graphs. So what are these? These are graphs which are embedded on a surface. Bipartite means that there are two kinds of vertices. Let's call them black and white. And that's also nicely, it is nicely embedded. So that means when the graph is embedded, if you cut along the edges, what you're going to be left with after cutting along the edges is a disjoint union of regions that look like disks. So that's a condition. It has been nicely embedded. Okay, great. So there's a lot of mathematics around these bipartite graphs. So here are some examples of these bipartite graphs and how they are described by a pair of permutations. So the way it works is that the edges are labeled from 1 to n, and the graph is drawn in such a way that as you go, so you pick an, imagine this is existing on a surface, you choose an orientation on the surface. So for this graph, I use the orientation of the surface, I go around the black vertices. So 1 goes to 1, 2 goes to 2, 3 goes to 3. That's the identity permutation. White vertices, same thing. And so I have a pair of permutations, one for the black vertices, which is the identity, one for the white, which is identity as well. Pair of permutations describes a graph. Here, if I go around the black vertices, I get 1 goes to 1, 2 goes to 2, 3 goes to 3. Here I get 1, 2, 3. 1 goes to 2, 2 goes to 3, and back to 1 when I go around. So that's a pair of permutation, which is like this. So you can get quite complicated graphs. So for example, if you have 1, 2, 3, 1, 2, 3, or 1, 2, 3, 1, 3, 2, this is a graph, 1, 2, 3, and 1, 3, 2. So that's this graph corresponds to this pair of permutations. Here, I have to get 1, 2, 3. So 1, 2, 3. But here I have to get, I want to get, when I go around here, I want to get 1, 2, 3 again. So I want this edge, which is labeled 2, to come next to this edge, which is labeled 1. So it has to go here. So in fact, it cannot be drawn on the plane without intersection. But imagine I was drawing a little handle here that lifts off that. Then this is a genus 1. It can be drawn on a surface which has a little handle sticking out here. So this is a genus 1 graph. This is a genus 0 graph. So there is, you can draw a graph of any genus, and they are all described by permutation pairs. And you know which pairs are describing the same thing if the pairs can be simultaneously conjugated by permutations. So now there's another triple. Given that pair tau 1, tau 2, you can say tau 3 is defined to be the product inverse. So now I have a triple of permutations. And that triple of permutations multiplies to 1 by definition. And the equivalence that I talked about, conjugating tau 1, tau 2, if I conjugate tau 1 and tau 2 by the same gamma, I will also conjugate tau 3. This follows from this. So I'm looking at triples, which are obey this equivalence relation. and they multiply to 1. So that has a nice geometrical interpretation in terms of this problem classifies branch covers of the sphere with 3 branch points. And the way the nature of the branching at the 3 points is related to tau 1, tau 2, and tau 3. So we have a surface which is mapping to the sphere. And these are very interesting surfaces called Belyi maps. Great, so that's sort of going from these colored graphs to other related combinatoric structures, which are of interest in string theory. Now we're going to move on to Fourier transform on that algebra of graphs. Okay, so we had a double coset, and then we reformulated in terms of pairs, tau 1, tau 2 with a simultaneous conjugation. And how many distinct equivalence classes we have here is again the number of ribbon graphs, which is given by the formulae that I showed you before. The number of ribbon graphs with n edges has a formula in terms of symmetry factors of partitions and a formula in terms of Kronecker coefficients. Now, given this description in terms of permutation pairs now, I'm going to move to the group algebra. So now I'm going to start thinking about linear combinations of sigma tensor sigma with complex coefficients. In this algebra, we can take it tau 1, tau 2, and we can ask, first of all, given a tau 1, tau 2, I can ask how many distinct tau 1 prime, tau 2 prime are there, which are related by this gamma conjugation. That defines what is called an orbit. It's an orbit in Sn cross Sn. It's all related to a given pair using that kind of gauge symmetry, if you like. So what I can do is I can take this algebra Sn, this permutation pairs in the first instance, take the permutation pairs and organize it, which pairs belong to the same equivalence class, which ones are indifferent. So you organize the whole Sn cross Sn into orbits, and I'm going to take an index R, which is an index over the distinct equivalence classes, or these distinct orbits. So for each such orbit, I pick a permutation pair, tau 1 for that orbit, tau 2 for that orbit, and then I sum over all the conjugates, the simultaneous conjugation. And I get a vector which lives in the group algebra of Sn, tensor the group algebra of Sn. Because I'm taking sums of things here, now I'm in a bigger space, I'm in group algebras. And that formula can be rewritten here. There was a sum over all group elements in Sn, 1 over n factorial. A little bit of group theory shows that that is equal to sum over all the distinct pairs in the orbit. So this is a pair in the orbit. A runs over the distinct pairs in the orbit, and this is 1 over the size of the orbit. So this is a very nice thing. All the distinct pairs which are in the same orbit, you just sum them up, divide, take an average, and this is what I call the geometric basis for K of n. There's a Fourier basis, which is labeled by Young diagrams. It involves 3 Young diagrams. dr1 is the, so for each Young diagram, there's a representation. The d's are the dimensions. And then there are 2 things here. It's complicated, but there are 2 things essentially. There's a drij that corresponds to taking the permutation sigma, going to the representation R1, and taking the I and j are state labels. So in this representation, sigma 1 is an operator acting on this vector space. Take the ij matrix element of that operator. That's what the d's are. And then these guys, which involve 3 representations, they are Clebsch-Gordon coefficients. So when you have R1 and R2, you can take the representation R1, tensor the representation R2, which has a basis, R1 I1 and a basis R2 I2. But it also has, because there's a typo here, that should be, that's a ket, that's a bra. So you have a basis of this kind, the product basis. But if you decompose this under the diagonal, so let the sigma acts here. Sigma is a group element. That's sigma tensor sigma. It acts here. That defines a well-defined action on the tensor product. Decompose that under EREPs. You're going to get R3, some state label for that R3, and some multiplicity index. And if you take the overlap of this guy with this product basis, you get what are called the Clebsch-Gordon coefficients. So things we know from physics. So you choose nice orthonormal bases here, nice orthonormal bases here, and then you have an expression like that, and you get a Fourier basis, which has very nice properties. These are the nice properties. You take this Fourier basis, if you conjugate by gamma tensor gamma, you're going to get back the same thing. This is saying that this lives in that algebra K of n. And that algebra K of n, it can be thought of as the subspace of C of Sn tensor C of Sn, which is invariant under this diagonal conjugation. So this object here, something in C of Sn tensor C of Sn, if you take, so let's say mu inverse here, mu tensor mu inverse on the sorry, mu tensor mu on the left, mu inverse tensor mu inverse on the right, this is going to be invariant because the mu's can be absorbed into the gammas. So we're looking at this algebra can be thought of as the subspace of here, which is invariant under conjugation by gamma tensor gamma. So the Q also lives in that invariant subspace, which is K of n. But more than that, the Q's, they multiply very nicely. If you multiply them, if you have Young diagrams R1, R2, R3 here, R1 prime, R2 prime, R3 prime, the product is 0 unless these triples are the same. And then you get a delta function on the taus, and then you get a matrix. You get the Q with tau 1, tau 3. So the structure of the tau here is just like multiplication of elementary matrices. And this formula shows you that the Q's have given you a basis for K of n, which maps that algebra K of n into a direct sum of matrix algebras. So it's called a Wedderburn-Artin block decomposition. The blocks are labeled by triples of Young diagrams, and the size of the block is C square. Tau 1 and tau 2 are these multiplicity indices. They are how many times R3 appears in the tensor product of R1 and R2. So using group theory things like tensor products, you can describe the matrix block decomposition of K of n. So to summarize, there are two important things here. There's the geometric basis and there's the Fourier basis. Great. So now we're going to define what is called the Fourier, what we call the Fourier subspace of algebra for a given triple. Fourier subspace is just labeled by triples of Young diagrams. And what is it? You take the Q's, you just take a direct sum over all the different tau 1, tau 2. So this one doesn't care which tau 1, tau 2 I'm thinking about. I'm thinking about arbitrary linear combinations of these basis guys. So that's a vector space of dimension, which is equal to the number of tau 1s and tau 2s. Number of tau 1 here is the Klebsch multiplicity of R3 in R1 tensor R2. Number of tau 2 here is the Klebsch multiplicity again. So that's C square, the Kronecker coefficient square. So the dimension of that is the Kronecker coefficient square. Now, this is all fine. You know, you can describe, write a formula for it. But one of the important things is that this formula is rather complicated. Working out explicitly these matrix elements is complicated. Working out the Klebsches is complicated. Choosing a basis and so on, that's complicated stuff. But we didn't use all that complicated stuff in proving these two properties. We just used the fact that there is an orthonormal basis, which we know exists. There is an orthonormal basis here, which we know exists. And using these things, you can prove these nice properties. But now we're going to take advantage of the fact that this is all happening within an algebra, which has another nice basis, which is this combinatoric basis. And the other thing we're going to use is that there are nice operators in the group algebra of Sn. So think about the conjugacy class consisting of permutations with a cycle structure, one cycle of length k, remaining cycles of length 1. Then if you take all the permutations within that conjugacy class, you get something which is in the group algebra of Sn and which is central. It commutes with all Sn. Now, for each such central element in Sn, there are 3 interesting operators in K of n, tk1, tk2, and tk3. And what do these look like? Okay, before I get to what they look like, one more thing about these t2, t3 up to tn. They are very interesting things. One nice thing about them and this is proved in the paper with Gary, which I mentioned at the beginning of the talk, there is some integer for every n. There is some integer for generic n anyway, n bigger than 2. There is some integer k star less than n, such that T2, T3 up to Tk star generate the center of the group algebra. And also, this is related to the fact that if I take the characters in representation, a fixed representation R of all these guys, and I take this normalized character, this is the character divided by the dimension. If I take this list here, and I compare this list from one Young diagram to another, that list is always going to be different. These lists completely distinguish Young diagrams. And this is related to the fact that this T2 up to Tk star completely generate the center. So using this, we have a nice way using these cycle operators, if you like. I call them cycle operators because they have one non-trivial cycle. These cycle operators nicely distinguish, and their eigenvalues nicely distinguish Young diagrams. But now we're in K of n, which is a bit more complicated. It's C of Sn, tensor C of Sn. So there we have three operators. Given Tk, you can let the Tk act on the first slot, you can let it act on the second slot, or you can let it act on both. So these are all elements in C of Sn, tensor C of Sn. Here I am taking the same element acting simultaneously in both slots. So there are these three operators here. This is a typo here. This is all Tk1, Tk2, Tk3. So there's Tk operators, which they are nice operators. K of n is a state space. It has a nice inner product. These are Hermitian operators in that inner product. So they can be used for building Hamiltonians. And the other nice thing is that when you act on these Fourier basis elements, Tk1, Tk2, Tk3, these guys, they just measure the normalized characters of the characters of Tk in R1, character of Tk in R2, character of Tk in R3. So, so these are all eigenstates, and notice these eigenvalue equations don't depend on tau. For any tau, this will be the eigenvalue. And but we also know that if we take enough of these t's, T2 up to Tk star, these guys can distinguish Young diagrams. So they can distinguish the label R1. These guys can distinguish the label R2. These guys can distinguish the label R3. So we can build normalized characters from all these Tk1 and so on. And this list of things, this list of operators, will be able to distinguish the Fourier subspace, which is labeled by a triple of Young diagrams. Now there's one more thing. If you use all these TKs, 1, 2, 3, 2, 2k star, it's a little bit of work to show, and we show it in the paper. You can choose integers in front of each of them, such that this one operator now can distinguish all the three labels. If you make kind of unwise choices of these coefficients, there could be degeneracies, but if you choose them right, then this Hamiltonian, this one Hamiltonian, which is built out of all these t's, can distinguish these R1, R2, R3. Distinguish, I mean that these will have eigenvalues which are written in terms of these normalized characters. And if these two eigenvalues are the same, can only happen if the triples themselves are the same. So great. So the nice thing is that now we can use these Hamiltonians in order to find the Fourier subspace inside K of n. But the K of n also has this combinatoric basis in terms of ease. So what do these operators look like in terms of this combinatoric basis? Well, they're actually quite simple. Take these combinatoric, conceptually anyway, quite simple. These are operators, when you multiply on a combinatoric basis, you get some integer. You get a matrix which is made of zero, either the matrix element is either 0 or some positive integer. And you get another combinatoric basis element here. You sum over these basis elements. And what are these integers? It all has to do with orbits in Sn cross Sn, right? So and this is a list of permutations that we're going to multiply. Well, it's a sum of permutations, and there's a list of things appearing there. So this integer is the number of times the multiplication of the elements in this sum with a fixed element in the orbit R produces an element in the orbit S. It's manifestly something which is either 0 or positive integer. So this is a positive integer or non-negative integer matrix for each of these operators. So now we are thinking about the Hamiltonian, which is made out of combination of these TKIs. Correspondingly, in this combinatoric basis, you have a linear combination of these integer matrices. So that's a matrix which we are trying to diagonalize in order to find the eigenvalues and eigenvectors. That's what we would do in quantum mechanics. So then the nice thing is, well, actually the eigenvalues we know. So we know it as an expression in terms of normalized characters. So the eigenvalues we know because the TKIs, their eigenvalues are these normalized characters. And I think last time I mentioned there are nice combinatoric algorithms having to do with labeling a Young diagram R with some numbers which depend on the structure of this partition, and you can work out the characters, called the Monahan-Nakayama lemma. So you can work out the character, you can work out the dimension using nice combinatoric steps. So we know, therefore, the eigenvalues. We know these eigenvalues in terms of known combinatoric things from SN group theory. And what we're trying to do is find the Fourier subspace, those vectors inside K of n which obey this equation. X acting on the vector must produce this combinatoric eigenvalue. But that I can slightly rewrite it. It's X minus the identity times this eigenvalue acting on the vector V must give me 0. So to find the Fourier subspace, the vectors in the Fourier subspace, we're trying to find the null vectors of this integer matrix. X was made out of these M's. The M's are integers having to do with how the TKIs act on the combinatoric basis. So that's an integer matrix, and I just want its null vectors. And when I found all the null vectors, I will have found a basis for this Fourier subspace. So whenever you have an integer or rational matrix and you're trying to find the null vectors, it is known that you can find a basis for the null space made out of vectors which are themselves integer vectors. And the way you do that, so here's this X. I can take the transpose of that matrix and I find its Hermite normal form. Finding that means finding a matrix U and a matrix H. H is a matrix of a special triangular form called Hermite normal form. U is an integer matrix with determinant plus or minus 1. X transpose can, for any square or rectangular matrix, there is rectangular integer matrix, you can find a Hermite normal form, which means you can express it in this way. And there are integer algorithms for doing this. It involves starting with the matrix you have, this X transpose. You can do swaps of rows. You can swap 2 rows, multiply a row by -1, add an integer multiple of 1 row to another. These are algorithms you can do. And each step of the algorithm amounts to building up this U, this unimodular matrix. And the outcome, this Hermite normal form H, amounts to finding a matrix with a special form, upper triangular, going along the rows. This first row starts with a non-zero number here, 1. The next one must start with a non-zero number, which is beyond where this starts, and this one is beyond where that one starts. and these numbers are less than this number. So there's some constraints on what a Hermite normal form is, and the standard integer algorithms are producing that Hermite normal form. And for us, what is important is that when a matrix has null vectors, when you try to find its Hermite normal form, there'll be a bunch of zeros here, and there'll be a corresponding row of zeros. And when you look at the corresponding rows in U, you will find just in the rows of U, you will find these rows form vectors, which are the null vectors of the original matrix. So there is an integer matrix algorithm, therefore, which produces the null vectors, and the number of these null vectors is equal to the dimension of the null space, which is C squared. So to summarize, we started with an integer matrix related to a Hamiltonian problem. We perform integer row operations, and we arrive at the null vectors. We count the null vectors, we get C squared. And these C square vectors, now you can take integer linear combinations of them. That will generate a sublattice inside this lattice. Okay, so therefore we can say that C square is related to a sublattice. Okay, so we've talked about constructing C square in terms of sublattices. What about constructing C, the Kronecker coefficient itself? There's a nice answer to that. There's an operation on this K of n algebra, which is an involution. S square is 1. It acts very simply by inverting two permutations, which represent an element in K of n. So, for example, given a pair of permutations, you can say, suppose I invert it. Is there a gamma such that this equation is satisfied? Are the inverses related to the original guys by this equivalence? If they are, then this operation S, which is essentially defined in terms of this inversion, then this guy maps ER to ER. This is the combinatoric basis vector. If it's not the case that the inverses are conjugate in this sense, then this guy and that guy will belong to distinct orbits under this simultaneous conjugation. And then if I invert that again, I'll go back to the same element. So what this will do, this S operation will either leave an orbit unchanged, or it will pair up orbits. Some non-self-conjugate ribbon will be mapped to another one, and they will form pairs. So you can think about, how does S act on the combinatoric basis? How does S act on the Fourier basis? And you can follow, using the formula I showed you, what happens when S acts on the Fourier basis. Turns out it leaves R1, R2, R3 unchanged. All it does is it swaps tau1 and tau2, these tau indices. As a result, the S equals 1 eigenspace in the Fourier subspace kind of is made of the diagonal parts and then the symmetric parts, symmetric off diagonal parts. So in total, the S equal 1 eigenspace has dimension C plus 1 over 2. Now that means I should, if I want to build these vectors, I need to use my Hamiltonian to select out this Fourier subspace, and then I can select out S equals 1, and I can build a rectangular matrix and look at the null vectors of that matrix. And that'll give me null vectors, which if I count them, I'll get CC plus 1 over 2. And the S equals -1 subspace, you get CC minus 1 over 2. Again, you can get them using integer matrices, and you can get a sublattice, and you get a basis for that sublattice. So essentially, I have one set of lattice vectors, which I count them, I get this. Another set of lattice vectors, I count this. So I have a small set and a big set, and I choose an injection of the small set in the big set, and what is left is the difference, which is C. And that gives us a construction of C itself. An interesting corollary of these properties of this S operation is that the number of self-conjugate ribbons is equal to the sum of the Kronecker coefficients. The sum of squares was giving you all ribbons. The sum of C's gives you the number of self-conjugate ribbons. Okay, so these are some interesting questions about constructing Kronecker coefficients. A couple of comments on the physics applications that I mentioned at the beginning. So imagine you've set up this quantum mechanics where you have all the states of K of n available to you, all these operators I talked about available to you, and for each ribbon graph, you've got a vector. Take such a vector, take the Hamiltonian that we talked about, apply the Hamiltonian and evolve it. This vector can be expanded in the Fourier basis with some overlap coefficients between the ribbon graph vector and the Fourier basis. Apply the Hamiltonian. This is just a number, so this applies here. H on that Q gives you the eigenvalue. So you had either minus I omega t. Now imagine you have this evolving ribbon graph, which is a time-dependent thing. And you can say in that time-dependent signal, have I got, for a given R1, R2, have I got that time-dependent component in the Fourier analysis? Okay, this is ordinary Fourier analysis now in time-dependent signals. Have I got that signal? If I have got that signal, that means that this Q must be non-zero. But this Q only exists if the Klebsch Kronecker for R3 in R1 tensor R2, if this Kronecker for this triple is non-zero, because tau goes from 1 up to Kronecker. So if the Kronecker is 0, this doesn't exist. So if you see this signal, that means this Q exists. So would be an experimental check that this guy exists, or in other words, this Kronecker coefficient is non-zero. Of course, if you find this does not exist, you don't find this signal, could be because for the graph you happen to choose, this coefficient, this overlap is 0. So just by studying one graph, you don't know whether the Kronecker is not 0. But you don't know, you can't say for sure that the Kronecker is 0. But if it is not 0, it is possible that you pick a graph, you find a signal, you can say, yes, this is actually non-zero. So the question about vanishing of this Kronecker is very interesting for complexity theory. Determining in general whether C vanishes or not for a triple of Young diagrams for some large number of boxes is a computationally hard problem. So this kind of the point here is to suggest that if we think about K of n and the quantum mechanics on it, K of n was sort of intrinsically constructed using Kronecker coefficients and such. So perhaps not too surprising, we should expect that this kind of quantum mechanics should know something about the vanishing or otherwise of Kroneckers. So this is an avenue where we could explore that. There's a membrane interpretation where each graph, each graph corresponds to a covering surface. The covering surface is a two-dimensional surface. Now, in our quantum mechanics, we have time evolving graphs. You could start with one graph, which corresponds to one string worldsheet. The graph evolves. As we saw for the Hamiltonians we discussed, the eigenstates are these Fourier bases, these Fourier elements of K of n. The combinatoric bases are typically not eigenstate. So therefore, they are not stationary states. They will evolve into some linear combination of graphs. And what is a linear combination of graphs? Where each graph corresponds to a string worldsheet. So now you have a superposition of worldsheets, and then it's all evolving in time. So you kind of have, a two-dimensional surface. Classically, if it evolves in time, you produce a membrane. So here you have a string worldsheet evolving, but at a later generic time, it's a superposition of worldsheets. So it's kind of a quantum membrane world volume. And depending on the combinatorics of this, typically the genus can change. If you start with a genus 1, genus 0, you might get a genus 1. There's a very interesting dynamics which has a membrane interpretation. So I think the final conclusion is just that, finite Hilbert spaces with algebra structure have a lot of interesting physics in it and mathematics. So I'll stop here.
Thank you very much, Sanjay, for a very interesting talk that spanned from foundations to applications. Very, very nice. Thank you very much. We had already a few questions in between. Ilya, do you know if there are more questions or people that indicated they would like to ask questions?
So far, there is none. Maybe if the attendees want to ask their question, they can raise their hand. Okay.
Yeah,
there is a question from Gary. Okay. Gary, you can talk.
Hi, guys. Can you all hear me okay?
Yes, we do. Thank you.
Yes, Gary, we can hear you.
Hi, Sanjay. Thank you for a great talk. So could you just explain maybe, just one more time, the connection between the null space of these Hamiltonians that you constructed and the Kronecker coefficients? The C-squared story, I think I understood.
Yes.
Okay, because that was sort of the dimension of the algebra of I think of the K of n. But then
that's right. So the sum of C square was the dimension of the algebra. And for a given, and that corresponded, so let me share my screen and I'll talk, but feel free to interrupt me as well as I explain this point. So how do we go to this null vectors? So the first point was that we have this sum of C square, which is the dimension, this n was the dimension of K.
Right.
Now, then the next point was that there is a basis for K. Well, there are two bases for K. One, this combinatoric basis, which is kind of directly related to permutation pairs, and the number of these is equal to that or equal to that. It's the number of ribbon graphs.
Yes.
And there's another basis, which is the Qs.
Right.
And there is a triple of Young diagrams, and tau 1 and tau 2 each run from 1 to C. So for a fixed tau 1, tau 2, tau 3, the number of things enumerated here is C square.
Right.
And then I defined the vector subspace of K of n, which is spanned by all these guys. And that's the Fourier subspace for a given triple. Then I say, I am going to look at these Hamiltonians, these TKIs. Yes. And the TKIs have the property that when they act on these Q bases, you get these normalized characters.
Yes.
And this equation on the right, and the eigenvalues just depends on the R's. They don't depend on the tau. So for whichever tau 1, tau 2, I would get these same eigenvalues.
Right.
Now, so the idea is that using that fact, I want to fix the look at all the, now I'm going to go to K of n and look at all the vectors in K of n which have these eigenvalues. Now, if my set of T's can be chosen such that the corresponding eigenvalues uniquely determine the R's, okay, then so maybe the main thing to say is that using these guys, I build a Hamiltonian,
yes,
whose eigenvalues I can write.
Yes.
But the important thing is that, let me make a note here. So H, there's one important step, which is that so if I ask what are the possible eigenvalues of H, the Qs, they form a complete basis, R1, R2, R3, tau 1, tau 2. So what are the possible eigenvalues? Well, I can think about the eigenvalues by acting on this basis, and I get things like omega R1, R2, R3. Whatever the tau is, the eigenvalues are insensitive to the taus. So these are the eigenvalues. Now, suppose I've chosen my Hamiltonian such that if omega R1, R2, R3 equals omega R1 prime, R2 prime, R3 prime, then these triples are the same.
Yes.
So then I can, if I fix the eigenvalue, I fix which subspace I'm thinking about.
Okay. Okay.
Right? It's like the triples form a label, and I have a Hamiltonian whose eigenvalues depend on that label. And each value of the label has a unique eigenvalue associated to it. And once we've got there, then we just say, take the Hamiltonian and find its eigenspace. And finding that eigenspace amounts to finding, this is the matrix corresponding to the Hamiltonian, X, and take that matrix. That's the thing I want to solve. And I know a formula from group theory for these eigenvalues. So I subtract that and I look at the null vectors of that thing.
I see. I see. Okay. And then, the dimension of that subspace, that's what gave us the C squared.
And that'll give us C squared.
Yeah. Okay. Okay. All right. Thank you.
Thank you. Ilya, are there more questions?
I don't see any other. There is one more arm from Robert. Let's let the Robert talk.
Yeah, perfect.
Sanjay, you've got these, or you've constructed these null vectors.
Yeah.
So you'll have some matrix of integers, is that right? Some vectors.
Some vectors of integers, yes.
Yeah. Does this have an interpretation, this vector?
You mean, I guess, the linear span of all these vectors is the same as the linear span of the Qs. But there is no detailed map between the individual vectors and the Qs at the moment that I know of. Because the Qs give you a bit more extra structure. They give you this matrix structure. The vectors are just C square vectors. So in a sense, there is you've retreated from some of the detailed information in the Qs.
Yeah. So is there anything special about this algorithm that you've got to get these null vectors? Are they exploiting anything? Or is it just a very general algorithm not tailored to this problem?
I guess in order to make contact with these integer algorithms, we're using the fact that this K of n is an interesting state space. It's a Hilbert space. It's an algebra. And one important thing that has gone on here is that the structure constants of that algebra are integers. And the fact that the TK is acting on the combinatoric basis gives you this integer matrix M. You see, the TKs are themselves elements of the algebra. So in fact, it is true that whenever an element of the algebra acts on another element of the algebra, you re-expand it. Those coefficients can be expressed in terms of these nice integer objects having to do with multiplication of orbits. So I think it's kind of using the fact that it's an algebra which happens to have a basis where the structure constants are integers.
Fascinating, Sanjay. Very nice talk.
Thank you, Robert.
Okay. If there are no more urgent questions, we all know how to reach Sanjay.
Yeah, absolutely. Please, yeah.
That means, and so we will do that, because I'm just worried about the time. And so Sanjay, now I think it's up to me to thank you for an incredible effort this week. I think this is the NITheP online webinar world record, 2 in a week. Next year, you will have to do a colloquium, a webinar, and a mini school. And so you can keep your outstanding contribution to NITheP. So thank you very much. Thank you to all the participants. Thank you, Ilya, as well. And we'll hope to see you all soon again. And hopefully, Sanjay, very soon you will be able to visit us again for real.
Yeah. Thanks a lot, Francesco. I really enjoyed giving this talk. Thank you very much.
Thank you very much. It was
Thank
great
you.
to have you.
Thank you,
Thank you very
Ilya.
much. Have a good afternoon, everyone. Yeah, all the best. Yeah.
Okay.
Bye.
Thank you.
Bye. Bye. Cheers.
Bye.
Bye.